Now, this next lab that we're going to do is, let me give you the correct number. I think this is number 3 in the sequence. Yes. This lab is number 3, and I'm trying not to move around too much because I noticed the last recording was very jerky. So I've got to keep my head steady. Waters of constitution and hydration. All right. The real purpose of this lab is to determine where the water comes from in a molecule, in a formula, and how to calculate how much of the water is attributed to a particular formula. Right? And water can occur in 2 different ways, 2 different places. I'm going to go over here and we're going to look at the board. I might have to tilt my head back a little bit so you can see it. This is Waters of Constitution and Hydration lab, and I've set up a table here, and this is what you should do in your lab notebook. In addition to writing a little introduction, safety, and procedure, then you need a place to put your data, and this is a good way to do it. Set up a table, just like this, and put blanks in there for information that you're going to collect. That way, if you are in the middle of your experiment and they're in order, and you run down here, and you find that you've missed a place with data, then you better stop and determine whether or not that data needs to be acquired, or for some reason, has to be a valid reason, you did not collect that data. All right. So we're going to fill in all of these places, and we need to get started because it takes a little time to do this experiment. All right. So we're going to do the first part of the experiment is part B. We're skipping part A. And don't forget to do the pre-lab question. Part B is the thermal decomposition of an unknown hydrate. Well, the unknown hydrate, I'm going to tell you what it is. It's a hydrated version of copper sulfate. All right. So this part, we need copper sulfate. And here it is, copper sulfate. And it's a blue color. Maybe you can see it. It gets blue like that when it has water in it. Okay. The other part, I'll show you while we're here, is the thermal decomposition of sodium hydrogen carbonate. Now, copper sulfate has water of hydration. That means that the water molecules are intact, separate, but attached to the copper sulfate molecule. Whereas the waters of constitution are incorporated into the formula of sodium hydrogen carbonate. And you don't see the water in the formula until you heat it and drive off the water and leave something behind. That's the difference between hydration and constitution. Okay, we're going to need some things. We're going to need a ring stand. We're going to need a ring. Yes. And that holds our little clay triangle, like that. Now, why do we need a clay triangle? Because we are going to place in that clay triangle, and I need a pair of tongs. We're going to place in that clay triangle our crucible. And in that crucible will be either the copper sulfate hydrate or the sodium hydrogen carbonate that we heat to drive off the water. But we need to do it in an orderly fashion. All right. So first thing we need to do is set up our desiccator. This is a desiccator. A desiccator is a device into which you put something, and you want the atmosphere to be completely devoid of water. And in our case, we're going to put something in that desiccator that has been heated. we want it to cool down in such a way that it does not reabsorb water. So we cool it down inside the desiccator where the relative humidity is 0. Okay, so we need a desiccant, something to absorb the moisture. And if I can get this thing open, it's not cooperating very well. There we go. This is Dryerite. It's basically calcium sulfate. And when calcium sulfate absorbs water, it becomes gypsum. Same stuff that's in your walls in your house, gypsum board. But right now, it's blue because there's an indicator in there. And when that indicator turns pink, that means it's absorbed all the water that it can handle. But at this point, our desiccator is set up so that we have a dry atmosphere in there now. Okay, next step is to be sure that our crucibles are completely clean, right? So in order to do that, we have to heat them dry. All right, so we need a flame. Oops, I had to turn on my gas. So let me do this as smoothly as possible. All right, we'll get there. There we go. Now we can turn on our gas. Strike it. And we need a better flame than that. There we go. We want to bring it down just a little bit. There we go. Okay. So the method says heat for 5 minutes. Put the crucible in there. Put the lid on it with just a little bit of space for any moisture to escape. So we put it on like that. There we go. Then we put the flame under it, and that's pretty well adjusted. The hottest part of the flame is right under the crucible, right? So 5 minutes, 11:35, we'll be done with that one. Okay, while we're here and waiting for that to heat, there are some other things. We're going to take our compounds and put them over here by the balance because we need to measure the mass of each of our compounds with lots of accuracy, and we want to use an analytical balance, which gives us 4 decimal places of grams, or 1/10 of a milligram accuracy. Because the difference in mass between before we heat it and after we heat it is going to be rather small. Now, we're going to be heating the compound in one of these crucibles. One compound, the copper sulfate hydrate in this one, and the sodium hydrogen carbonate in the next one. How do you know the weight of the compound? Well, we do what's called, we measure the tare. We measure the mass of our crucible first. So then when we measure it again with something in it, all we have to do is subtract the mass of the container from the total, and we have the mass of the compound or the substance that's in the container, right? And we've set up our data table over there that I just showed you in such a way that we need to put in those values. Then we can do the calculations to get the other values. Okay. In the interest of time, I'm going to call this one done and move our crucible over here and our combustibles away from the flame. We don't want to get too close with the plastic. All right. So let's take this one and move it. We're supposed to let it cool for a couple of minutes. Let's do that. And while it's cooling, It won't be cool enough to absorb water. Now we'll move it into our desiccator. There we go. And we're going to set the lid off so it'll cool a little bit faster and cover it. One rule is the only time you uncover your desiccator is when you have to put something in or take something out. The rest of the time, it must have the lid in place. Why? Because when the lid is off, the desiccant, the calcium sulfate in the bottom of that desiccator, is sucking up moisture from the surrounding air. If you leave the lid off, in no time, your desiccant will be exhausted. So now we need to let it cool. This might actually take 5 minutes because you can't rush cooling. And you'll notice if you don't let it cool all the way down and you put it on your balance and it's still warm, then the balance will not settle down. It'll just keep drifting. So while we're waiting, let's talk about safety. All right, you need a safety blurb. So what about this whole procedure requires safety considerations? The first obvious one is heat. The burning gas presents a burn hazard, and anything that it heats presents a burn hazard. Touching anything that's come into contact with the heat or the hot crucible, that's why we use tongs to manipulate them. In addition, we use tongs because the difference in weight is so small. If you touch these things with your hand, even if they're cold, you have added weight by your fingerprints. The oils on your hand will bias the weight over what the actual weight is. So we want to handle things either with gloves if they're cold or with tongs if they're hot. All right, we're still waiting. So you will also need a spatula. This just has a special name. It's called a spoonula, right? Because it looks like a spoon. The kind of spatula that you normally would use would be, let's see, let me pull one out. This is actually a spatula. Yeah. It has a fat end and a narrow end. The narrow end is good for measuring out small amounts, right? And the way you hold it for delivering controlled amounts of your substance is kind of like chopsticks. You have these fingers holding your middle finger and your thumb holding in the middle of the spatula, and then you rest the back of the spatula in the crook of one of your other fingers, and that stabilizes it. And then to deliver, all you have to do is tap with your index finger, right? So that's called controlled spatula. Okay. Now, why don't I measure out that material while I'm waiting into, say, some other container, and then just transfer it into the crucible when I'm ready? Well, the problem is, once you get through heating your crucible and cooling it down, how are you going to separate that material from the crucible to accurately measure it? Because we measured it in some other container before, that just adds potential places for error. You want to minimize error all that you possibly can. So we're going to add the material directly into the cooled crucible after we weigh the crucible. We need to know how much the container weighs. Then when we add the substance into the crucible, then we can tell how much we've added by the difference in the two weights. Okay, let's see. If we feel that, we feel it's very warm. So my guess is that it's going to drift. But in the interest of time, I'm willing to put up with a little bit of drift, and we'll deal with that. All right, so let's carry the crucible over here with our tongs to the balance. There. The balance is zeroed. Right? You just push the tare button. It's zeroed. Now, what do we weigh? You weigh both the crucible and its lid. Why? Why would you want to do that? You really only need the crucible because that's what's holding the material. Well, here's why. When you heat that material on that flame, it might spatter. You know, as water comes out of the material, it may vaporize so quickly that it'll spit and spatter. And what that will do is it will deposit some of the material on the lid. So if it does that and you don't have the lid weight, then you've lost material that you think is water, but it really isn't. So you weigh both of them. And that is the value, the weight of your crucible. Okay, put both of them there. Replace the lid. And we're just going to have to pick a weight because it's going to drift. 35.1083. 35.1083. So we'll put that in our table here for the copper sulfate. That's the first one we're going to be doing. The crucible weight, 35.1083 grams. Okay. Now, the next thing we're going to do is add copper sulfate to it to within, let's see, the procedure calls for 1.9 grams. It doesn't have to be exactly 1.9, but whatever it is, you need to measure it accurately. So what would 1.9 added to this value be? It would be about 37. About 37 grams will be the value we're shooting for. So let's set this aside. And let's try to make 37 grams. Don't put too much because you don't want any falling on the balance. You want it in the crucible. Okay, and you can watch the scale move. That's the nice thing about electronic balances. You can watch the scale move as you add. Okay, we're coming up on 36 and on our way to 37. Getting there. A little more. It's okay if we go over. All right. Now, close the door because these balances are very sensitive to air movement. So to get your weight, the door needs to be closed. I'm going to clean off my spatula so I don't cross-contaminate. All right, 37.0518. 37.0518. Here we go. Now, wet weight, that is, how much does the hydrated copper sulfate weigh? Subtract the weight of the crucible and its lid, of course, from the total, and you get a value here for wet weight. Right? Can I do that in my head? Yeah, probably. 5, 3, 4, 9, 1.9435 grams. Okay, that was the first one. Now, let's remove the crucible and its lid. Actually, now we don't need to put it in the desiccator because we're going to heat it up and drive off the water anyway. Right, so let's set this here. It might be safer to carry it in the desiccator. Let's do that. Let's move it to the desiccator just so it's easier to carry. Here we go. Now, we'll let that settle down before we bother zeroing it. Okay. Now we can remove our copper sulfate and crucible. Set it aside. And now we want to remove the heat. Let's get on this other side. Here we go. We're going to let that cool down a little bit before we put it in our desiccator. It's only going to condense water on the crucible when the temperature drops below 100 degrees centigrade, because that's when the water vapor becomes water liquid. So we've still got a few more degrees so we can wait. But let's take it off of here and set it down here and start heating our copper sulfate hydrate. Very carefully. Set it in the triangle and then offset the lid to allow for water vapor to escape, but not enough gap to lose any material if it spatters. Now let's heat it up. And how long are we supposed to heat it? A minimum of, let's see, is it another 5 minutes? 10 minutes. So we're going to go 10 minutes. So 5 minutes till 12, we'll take that one off. All right, this one's cooled enough, I think. So let's move it into the desiccator. Take the lid off. Here we go. And we'll give it about 5 minutes, about half the time it takes to heat our copper sulfate. I don't know if you noticed, but I saw some steam coming out of that. It may not have been caught on camera, but there is steam coming from the material. Remember, the material started off blue, right? If we look at it as it heats, it's already around the edges started to lose that blue color. Okay? That's what's nice about copper sulfate hydrate, is that as it heats, it loses the blue color because the water, well, it's a long story, but the water makes it turn blue. That way you can tell when it's finished heating, even if you don't wait for 10 minutes. All right, while we're waiting, I'm going to smoothly give myself a drink. Now, I just did something bad. I have a drink in the lab. I'm the only one in here, and my drink is 20 feet away from my work area. So under these circumstances, I think we're safe. Although, technically speaking, it's the wrong thing to do. Couple more minutes, and we'll be able to get the tare weight, T-A-R-E, tare weight of our second crucible. Now, if we had a lot of crucibles and we were going to do this experiment multiple times, then we would want some way to mark the crucible with a number so we could identify it for each sample, because you don't want to mix your samples up in the process. Sorry for the shake. But there are very few things that can stand that heat. So what we'll very often do is we'll take an etcher, either a diamond stylus or a carbide stylus, either stationary or vibrating, and just etch a number on both the crucible and its lid. And there'll be a matching pair, and you can keep track of them that way. But since we've only got two, I think we can keep them safely apart and know which one's which. Let's see, we're coming up on 5 minutes. Let's take a quick look at our material. Oh yeah, it's getting there. Now, the nice thing about copper sulfate hydrate is it has a very wide range of response to temperature. In other words, the amount of temperature rise it needs to evaporate all the water is just a little bit, and then there's a big gap between that temperature and the next critical temperature, the decomposition of our copper sulfate. So we have a wide range, and it's good for student labs to have that range so that you can heat it with some variability and still get good results. So we're coming up on 10 minutes, or is that 5? That's 5 minutes. So we're going to heat that some more, and let's see how our second crucible is doing with weight. And notice when I say weight, I really mean mass. It's a holdover from the good old days when we weighed things rather than massed them. Mass was never used as a verb, whereas it is now. Okay, let's reset this to 0. Okay, now let's find the tare weight for this crucible. There. And its lid. There we go. 34, 34, 35. So let's put that in here. 2 34s and a 35. And that's for the second part, the crucible. 34, 34, 35, and that's grams. All right. Now we can, while we're waiting, measure out the sodium hydrogen carbonate. And let's see, what are they expecting? I think it's about 2.5 grams, if I remember correctly. Yes, 2.5 grams. And the accuracy, remember, here is 4 decimal places, which is 0.0001 grams. So let me get this out of the way. And let's see, what's 2.5 grams plus that is 36.8. So our target is 36.8 for this substance. Okay, I hope my head is positioned right so you can see what I'm doing. Otherwise, this whole video would be pointless. We're getting there. 36.45. Oops, I went over. That's okay. All we need is the accurate mass of the substance. 37.2256. Okay. And let's darken this one up a little bit. I kind of like that dark color. It's going to show up better in the photographs. There we go. Now, what's the weight of the substance, the sodium hydrogen carbonate, in the crucible? It's this difference. It's 1, 2, 8, 8, and 2. So let's see if that's right. 6, 5, 12, 11, and 1 is 12. 1 and 6 is 7. Okay. So now all we have to do is heat them both up. Well, we're heating this one already. And then after that one's done, we'll heat this one up and weigh them again. Okay. That heating is about done. So while we're waiting for it to finish, we'll go ahead and move this one for carrying purposes over here. We don't even have to put the lid on it. See, I've got some error introduced. I introduced some error. The spillage. So we just recognize that there's error there, and in the interest of time, we're going to let it go. All right, so let's go back over here. And oops, move this over here and take the flame away. Let it cool for a minute or two, and while we're waiting, take a look. Oh yeah, I think that one's done. It's ready to come out of the oven. So let's move it over here. Fortunately, I don't see any spattering. All right, there we go. Now let's move this one into the hot seat. Here we go. Don't spill it though. Don't be clumsy like your instructor. There we go. Now we can put it in the triangle. These crucibles have a name, by the way. They're called Gooch crucibles. Gooch. Probably named after somebody. So now let's move this one. I'll tell you what, let's take the lid off. There we go. And let that finish cooling down in a 0% humidity environment. Now let's move the heat back under this one, center it, and check our time. So about 8 minutes after 12, this one should be good to go. Now, suppose we were, while we're waiting, suppose we were going to use gloves. All right. How would you use gloves? These are the last ones there. Okay. These are nitrile gloves. We use nitrile because latex sparks allergies in some people. So these are nitrile gloves. And everybody knows how to put a glove on, probably. Just get it on your hand like that and bring it down. Okay. Now there's a pair. Here's one right there. Okay. We're not using gloves for this experiment. But gloves are a good thing. All right, they protect your hand. They add another layer of protection should you be dealing with anything that's hazardous or even hot, because these gloves will withstand a little bit of temperature before they melt. It gives you some protection. But if your gloves are contaminated rather than your skin, what do you do when you're finished with them? How do you get these gloves off your hands without contaminating yourself in the process? Well, there's a procedure, right? You want to turn the glove inside out so that the contamination is on the inside of the glove now when you throw it away. So you grab one here, not against your skin, because this may be contaminated. So you grab it here, pull it off like that. Then you wad it up in the palm of the other glove. Now this is a clean hand on clean skin. You go underneath the second glove and invert it like that. And now you've got the contamination contained. Okay. And we still got a good ways to go. The thing about sodium hydrogen carbonate is you can't tell when it's done by color. Sometimes you can judge the appearance because it'll become more granular as it heats. This has still got a long way to go. It might take more than 10 minutes on that one. But what we're going to do is we're going to take our copper sulfate and put it on the balance and see if it's stable. Okay, we're back down to 0. Good thing. Now we're going to get the mass of the crucible with the heated product inside. Okay. Hopefully it'll settle down. If not, we'll just have to guess. 36, 33, 39. 36, 33, 39. Okay. Now, how much does the product inside the crucible weigh? This has the product in it we need to subtract out the crucible weight. So here's the crucible weight. Subtract this from that. Can I do that in my head? 3 from 9 is 6. 8 from 13 is 5. Okay, we had to borrow one, so 0 from 2 is 2. And 1 from 3 is 2. And we didn't have to borrow over here, so that's 1. 1.2256 grams. So we've lost about 0.7 grams. Yeah, a little less actually, of water. So how do we know how much water was lost? Well, this is the weight of our product before it's got water in it. This is the weight of our product afterwards. It's got no water in it. So subtract this one from that one, and you have the mass of the water. I forgot to put a place for that. Okay. So let's see, subtract this one from this one. So this will be a 9. 5 from 13, 8. Nope, 5 from 12 is 7. I had to borrow one. And I had to borrow one up there, so that's 1 here. And this is. Now let's see if that's right. Add them together. 13, 1 and 12 is 13. 1 and 5 is 6. No, 1 and 2 is, plus 1 is 4. And 7 and 2 is 9. There we go. So this is how much water. Okay? So that table is complete. We need to finish this table. Let me see how much time we have. And we got a little bit longer. So let's deal with this data. What are we trying to do? We're trying to figure out the formula. Copper sulfate, we know what copper sulfate is. It's CuSO4. Because this is 2 minus charge, and that's a 2 plus charge, one of each. This is a polyatomic ion that you'll learn about in class. And then that dot says, this is waters of hydration. How many molecules of water per molecule of copper sulfate? We don't know yet. Right? But we do know that when we heated this, all of the weight loss was here. So that's why we can say this is the difference in weight, water. So how many moles, and this is the ratio, moles of this to moles of that. Right? So how many moles of water do we have? Well, let's see. Let me get my calculator around here somewhere. Here we go. Get my calculator right here, my scientific calculator. How do we determine the moles of water if we know the mass? Right? This is your dimensional analysis. Right? We want to convert that one to moles. So we need moles on top and grams on the bottom for our conversion factor. So grams will cancel and leave us with moles. So what's the ratio of grams to moles for water? Well, 2 hydrogens is 2 times 1.01, 2.02. And oxygen, H2O, right? H2O. So that's 2.02, and this is 16, so it's 18.02. All right. So if we divide this into this, that'll give us moles of water. So let's do 0.7, 18.02 is, actually I'm going to need a little more scientific notation. How many significant figures do we have? 4 here and 4 here. So we can have here 3.984 times 2 moles water. Okay, but we want to ratio the number of moles to the mole of copper sulfate. Well, we can't do it with this one because it's wet. We don't know what the molar mass of this one is because we don't know how many water molecules are there. But we do know this one, the decomposed weight, is copper sulfate, no water. We say that as copper sulfate anhydrous. So we do know what that one is. All we have to do is add copper, sulfur, and 4 oxygens. All right, so let's see. Copper is 63.55. And sulfur is 32.07. And oxygen is 16 times 4, which is 64. So that's 159.62. So here we have this one. Per mole. This is otherwise known as molar mass. The molar mass of sulfate is this, right? So we'll divide that into 1.2256, and we get 7.67 10 to the minus 3 moles of copper sulfate. So now the ratio of the two, this one to that one, will give us how many for every one of those, right? So we need water on top, 3.984 times 10 to the minus 2 moles of per how many moles of copper sulfate? 7.678 times 10 to the minus 3 moles sulfate. And that our X value. Okay, let's do that. Eight, 9 moles of water per mole of copper sulfate. Right? But this needs to be a whole number. So we've got to approximate that to the nearest whole number. Experimental error, that was probably, who knows? We could have measured something wrong. We could have not heated it long enough. Anyway, averaged out is equal to 5. So what's the formula? We have copper sulfate dot 5 waters. There you go. All right, so I just did that one for you. Your grade will depend on whether you take this information and put it in a valid report, because this one requires a formal report. Okay, I think it's time to check on sodium hydrogen carbonate and just see where we're at. All right. We're finished with this one. I don't know if this is right or not. It may require some time, a little more time. That could introduce a lot of error because this weight was higher than we should have. It was more than 2.7. It was actually 2.8. So if we go a little longer, that's a good thing. Let's give it a few more minutes. Now, the analysis of the data for the sodium hydrogen carbonate is a bit more involved than the one with copper sulfate. The reason being that water is not the only thing that can be liberated from the sodium hydrogen carbonate molecule. Besides water, it could give off carbon dioxide, for instance, right? Because sodium hydrogen carbonate has the potential to liberate carbon dioxide as well. So it takes a little more sleuthing to determine what has happened in this process. And that's why in the Blackboard course, in the folder, along with this procedure, with this document, is another document that describes the process, the logic behind all this. And hopefully you'll be able to deduce and create a report from that information based upon your experiment data. Well, in this case, my experimental data. So when I get the numbers, then you'll have numbers to work with. And I just broke my own rule and left the lid off. All right, so let's have to be extra careful now. Just need to close that lid. All right. There we go. All right, so while we're waiting a little bit longer, let's see, where's my wash bottle? My wash bottle, here it is. My wash bottle. Notice, if you can see this, when I add water to this material, what's going to happen? Immediately turns blue again. And we're going to let it sit there for a little bit to help us clean out the crucible. Chemistry is kind of like cooking. It's all in the timing. Except you cannot lick the spoon. I don't know how this one's going to go. Doesn't look very promising. All right. Okay, that's cooled off. Now we're going to use this as our waste container. This is copper sulfate. We don't want to put that down the drain. Okay, there's a little bit. Let's see how much we can get out with just rinsing. We don't want to have to scrape it. Although we can if we need to. All right. It's getting there. Oh yeah. Broke it loose. Okay. Now, if you don't have any time, you can just set this out and let it dry. And we want to rinse the lid out as well. Set that aside for proper disposal. Let's take another look at this one. Okay. Let's see. Oh, that's a good flame, all right. And the hottest part. All right, in the interest of time, we've already gone 20 minutes. In the interest of time, let's take this one off and let it cool. We're through with the burner. We can shut it down, set it aside, let that cool for a minute. And while it's doing that, we'll turn off the main gas. Okay. Let's move this over away from the heat. That's not the only thing that's hot here. Cool this down a little bit. Set the lid off. A bit like that. Okay. So now we want to let those things cool, obviously. Okay. That's about a minute. Go. See, there's not much difference between before and after that you can tell just by inspection. That cool. Let me get a chem wipe and turn this thing over so it can drain. There we go. That'll cool it faster. And separating these things from one another will cool them faster as well. Okay. Twiddle our thumbs time. Let's take our reagents here. Make sure they're sealed. Okay. We'll need the balance still, but we won't need these materials. Didn't use that, so it doesn't need to be wiped. I use this one. Okay. All righty. A clean balance is a happy balance. And I'll put these away for future use in another location, actually. Okay. Let's see. Let's come around here. The nice thing about sodium hydrogen carbonate is since the water was extracted from its molecular structure, it's more difficult for that water to return if we expose it to the atmosphere. It can still absorb water, right? The water can cling to the particles, but they won't go back into the molecule the way they were beforehand. So let's find out what the mass is for this product. Okay. 36.1, still drifting. 1540. 36, 1540. Okay, what's the difference between this one and the Crucible? Here's the Crucible. Okay, let's see what the difference is. So subtract this one from that one. 5 from 10 is 5. 3 from 4, actually 3 from 3, we borrowed one, is 0. 4 from 5 is 1. 3 from 11 is 8. We borrowed one, so 4 from 5 is 1. So you lost about a gram in the process. Okay. For sodium hydrogen carbonate, the difference in weight is not as critical to deducing what's going on, because the difference in weight is only partially due to a loss of water. We probably lost some gases as well, like carbon dioxide, or it could have been carbon monoxide. But that's why the extra document that I put in Blackboard for you discusses those possibilities. Let's go ahead and do the subtraction anyway, and we'll find out what the, this is the decomposed solid right here. And the difference between these two is the weight that was lost. So we could say this is not water, this is weight loss. Okay, so this one subtracted from that one would be 6. And we had to borrow one, so that's a 1. And then 7. And then 8 from 8 is 0, 1. So weight loss was a little over a gram. Okay. In the interest of time, I'm going to let you look at that document and look at the discussion. The discussion is very detailed, and it gives you possibilities, right? We're on a detective, a treasure hunt, because you don't know what could have happened from here heated, and you can end up with some solid plus water is a definite possibility, plus something else. It could have been carbon dioxide or carbon monoxide. So we give you that much. To discuss. So you look at the possibilities. What could the possibilities be for that solid? Well, if we lose water, we're definitely going to lose that hydrogen and another oxygen. So there are probably 2 of these, right, to give you 2 hydrogens. So if you lose water, then you're going to have sodium, and then you're going to have something probably with carbon in it. right? So it could be what? It could be sodium carbonate, right? That's a possibility. Or it could be, let's see, what's another possibility? Sodium carbonate. Or it could be sodium oxide. Let's see, this would be 2, right? Polyatomic ion, 2- charge. It's 1+, it has to have 2 of those. Same over here, this is 2-, so we have to have 2 of these. Some other possibilities are discussed in the document, but they're thrown out for other reasons. So we're really left with these 2 possibilities, this one or this one. Now, the one thing we didn't do was do a test, right? So the next thing you need to do, or I need to do for you, is to test the product, right? I didn't put everything out here I need, sorry. Need this to run our Fizz test. So what we need is hydrochloric acid. Let's see if I've got some in here. Nope, that's not it. That's not it. That's not it. Forgot to put it out. I have to go find some. Okay, let's do that. First of all, what kind of beaker do I need to run the Fizz test? Uh, 100 milliliter beaker and 30 milliliters of water. Let's see. I think we can get by with a smaller beaker. I do believe we need something to stir it with. We need a dropper and we need acid. Hydrochloric acid, 1 molar. There we go. So, there. We're going to need, what did I say? 30 milliliters of distilled water. So we need a graduated cylinder. Measure out 30 milliliters. And let's do it the hard way. There's 10. Coming up on 20. And almost to 30. Now this doesn't have to be exact, just in the neighborhood. This is a qualitative examination of the product of our last heating. Right. So let's keep that separate first. And let's transfer this material into the beaker. It needs to be dissolved. Now, why are we doing a Fizz test? Well, if we've narrowed down the products to either sodium carbonate or sodium oxide, then the Fizz test will tell us which one it is. Let's see. Spatula. I got one right here in my pocket. Okay, we're going to transfer. That's easy to handle. Fingerprints don't matter now because we're not going to weigh it anymore. So let's transfer that. There we go. And let's put our 30 milliliters of water in there. Dissolve it. Okay. Now, the one thing about sodium carbonate and sodium oxide is they are both water soluble. We get to the discussion of solubilities, we'll find that anything that's combined with sodium, a sodium salt like sodium carbonate, sodium bicarbonate, sodium oxide, Sodium chloride, any sodium compound like that. We don't know which yet. Okay. Then I think we draw out a milliliter. This doesn't have to be exact either. So what we need is something that'll approximate a milliliter. Now let's see. This transfer pipette is not calibrated. So since we need a milliliter of both, it means their ratio is 1 to 1. So it doesn't have to be a milliliter. It could be let's see. Here's another one, which has been thoroughly cleaned and is dry. So I just need to measure out exactly the same amount of each one. So let's measure this one out. Let's go up to the bottom of the bulb. How about that? Well, it's not going to be cooperative. There we go. Bottom of the bulb into there. Now I need to do the same thing with the hydrochloric acid. There we go, perfect. Now watch. Do we get a fizz? Bubbles. Whoa, yes we do. Okay, what does that mean? All right, I'll show it to you on the board. I'll draw you a picture. What happened to my, here it is, my marker. All right. We've already talked about this one, so let's erase this one. I'm going to erase this one as well. So what are we looking at? What happens when you put these in solution? Sodium carbonate in solution yields sodium ions and carbonate ions. Okay? Sodium oxide in solution goes like this. It actually reacts with the water. Right? So what it gives you is sodium hydroxide. Right? So we need 2 of these, and let's see. That is 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens, 2 sodiums, 2 sodiums. So we get this in solution. So what happens with this one when you add hydrochloric acid? Hydrochloric acid doesn't react with sodium. Well, it makes sodium chloride. But it doesn't give you a fizz. So what is that fizz? That means you've created a gas. So what happens is that, and you need 2 of those, yields, and this is an unbalanced, this is an extra charge. So actually, if we wanted to balance this one, we put that actually reacts and gives you carbonic acid in solution. Okay? So when we react these 2 together, we get water. Let's see. No, we get, actually, we don't need that. There we go. What we get is carbon dioxide, which is a gas, plus CO2 and one extra. Let's see. One carbon. We need 3 oxygens over here. So I guess we do need a hydrogen. But this is an unbalanced equation. And what you get is when you react that hydrogen with this, here, this is better. When you react that hydrogen with it, you get carbonic acid, lots of it. But this is very unstable. It prefers to be water, excuse me. It prefers to be water, 2 hydrogens and one of those oxygens, and the other makes CO2. That's your gas, all right? When you add hydrochloric acid to this one, all you get is a neutralization reaction, sodium chloride plus water. No gas. So that's how we differentiate between this one and that one. So on a qualitative basis, we have proved that the solid product is this one, not that one. Now, the document that I put in Blackboard also gives you a quantitative way. Why? Because this solid, where is it? This solid, if you take that and convert it to, let's see, we know how many moles this is because we know the formula. So it's that many moles. And that many moles decomposes to give you so many moles here. And you can compare those two, not that one, this one. Compare these two. This one's sodium hydrogen carbonate. Then you say, is this a reasonable mass for that one? Is it a reasonable mass for that one? Well, you know that this one should be heavier than that one because it has a carbon in it and 2 other oxygens, right? So the heavier one is the right choice. And the document discusses that in detail. All right, so we have all the information we need. We've done the Fizz test. This experiment is complete. Now it's up to you to generate a formal report. And what I'm going to do is when I stop this video, I'm going to take a Photoshop of that board. So I'll have the data. And you can extract it from the video. All right, we're done, except for cleanup, right? You have to clean up.